Understanding the mechanical system of a speaker is crucial because the components and their interactions directly influence how sound is produced. Essentially, a speaker, particularly its driver unit, operates as an oscillatory system comprising three main components: mass, damper, and spring. This setup is akin to many other mechanical systems where vibration is a key factor. The mass component encompasses various elements such as the diaphragm of the cone, the mass of the voice coil, the effective mass of other moving parts of the speaker unit, and even the added mass of the air that moves along with the cone. The damping effect in a speaker unit comes from the suspension system, which consists of the surround and the spider. It is important to note that the surround and the spider also double as the spring, working together to align the movement of the cone during the oscillation. The surround is the flexible ring that attaches the outer edge of the speaker cone to the speaker frame. It allows the cone to move back and forth while providing restoring force to center the cone when there is no input signal. The spider is another flexible component located behind the speaker cone, usually closer to the voice coil. It provides additional support to the cone while allowing it to move freely back and forth. The damping of the vibration is a result of dissipation of mechanical energy at the surround and the spider. Additionally, air friction contributes to increasing damping. Meanwhile, the spring effect comes from the stiffness of the cone surround and the spider support, as well as the air pressure from the compressed air inside the enclosure. Together, these components constitute a dynamic force balance for a vibrating system, characterized by this equation on your left, assuming a sinusoidal excitation by an external force, F. Here, m is the mass, c is the damping, and k is the spring constant. X is the excursion distance. F of t represents the external force, which in this context is the electromagnetic force generated by the electric current flowing through the voice coil. Once we've modeled the mechanical system, we can then explore how the speaker behaves in response to the input current from the amplifier. In the complex plane, the mass and spring components act on the real axis, representing the energy of kinetic motion and potential energy. Damping, on the other hand, operates along the imaginary axis, out of phase with the motion, and dissipates energy into heat. The solution for the displacement of cone, x, can be obtained by solving the above equation. Rd is a dimensionless response factor to make the equation look less daunting. Or does it still? At very low frequencies where the forcing frequency omega is much smaller than the natural frequency omega n, Rd is approximately equal to 1. It rises to a peak near omega n and approaches 0 as omega becomes very large. For the above three frequency conditions, the vibrating system is described as spring-controlled, damper-controlled, and mass-controlled, respectively, depending on which element is primarily responsible for the system behavior. This relationship provides the key to understanding how the mass and spring work together to impart a distinct resonance behavior to the system. When the forcing frequency omega becomes close to the natural frequency omega n, the system exhibits rampant oscillation. This resonance phenomenon is a result of the mass and spring exchanging the energy in a periodic manner at the natural frequency. It's the damping that controls this resonance that could otherwise lead to a divergence, where the vibration could spiral out of control. Damping serves as the stabilizing factor, ensuring that the system remains within manageable limits and preventing a system breakdown. To gain a proper control, the damping of the speaker driver is typically set at a relatively high level. When the driver is housed within the speaker enclosure, essentially the sealed box types, the air inside acts as an additional spring, adding to the equivalent stiffness of the system. Consequently, the effective spring value K increases, causing the resonance frequency to shift upward. This explains why the resonance frequency of a sealed box speaker is higher than that of a driver positioned in free air. The additional stiffness by the air in the box could also result in more pronounced excitation of the cone, requiring tighter control from damping. Therefore, the driver unit is typically overdamped, beyond what would be optimal in free air installations such as on an infinite baffle, to compensate for the strengthened resonance when the driver is mounted on an enclosed box. By incorporating a ventilation port of proper diameter and length, the speaker's bass extension can be enhanced, allowing it to reproduce deeper bass notes. Alternatively, ventilation ports may be replaced by passive radiators, which resemble the low-frequency driver of the speaker, or the woofer, but lack a voice coil. These radiators serve as dummy masses tuned to lower natural frequencies than the woofer itself, thereby extending the speaker's bass range. Also, the use of sound absorption materials within the enclosure helps control air oscillation, and hence increases overall damping of the system. The illustration to your left demonstrates how a mass suspended on a spring can behave differently as a result of change in the damping ratio zeta, or the fraction of critical damping, to put it more precisely. In the speaker society, the quality factor, Q, is preferred over the fraction of damping ratio, zeta. Although they come from different origins, these two factors can address the same issues and can easily be converted to each other by a simple relation, Q equals 1 divided by 2 zeta. When designing a speaker, the quality factor of Q equals 0.7 is often regarded as the reference point to start. This value provides a flatter frequency response above the resonance frequency, yet ensuring the bass is not overly compromised. Many sealed and ported speakers take the liberty of manipulating this value for a better tailored bass response. As discussed above, the dynamics of speaker diaphragm vibration become complex near the resonance frequency. While the resonance can make the bass sound louder, it can introduce difficulties in controlling cone movement, leading to a booming and unclear bass near that frequency, particularly in speakers with ports or passive radiators, which are inherently more challenging to manage than sealed boxes. Examining the three frequency regimes discussed earlier, we can infer that the mass dominates at higher frequencies due to its omega squared in the denominator we have seen above, amplifying its effect relative to damper and spring. At lower frequencies, the mass term becomes insignificant as the decreasing omega squared in the denominator reduces the influence of mass. It is important to note that the dominant force is the primary factor that constrains the cone movement the most. The stronger the force or control, the smaller the cone excursion will be. Resultingly, the spring term, kx in the above equation, dominates at low frequencies, as its magnitude remains unchanged while the importance of mass fades out. This means that at low frequencies, the spring plays the primary role in limiting cone movement, and the excursion is governed mostly by the spring force. The damper dominance occurs near the resonance frequency, between the mass and spring-controlled regimes, by regulating the competition between mass and spring exchanging energy with each other. A well-damped system can provide an optimal performance with clear and controlled bass, especially in the transient response. An impulse signal can often result in sustained reverberation in the bass as a result of insufficient management over the added ports or passive radiators, which is often more difficult than handling the woofer alone.